All right, so let's talk about now sensors and signal conditioning. This is part of the module 2 of the measurement and instrumentation course that we're studying. So far we have seen basics about measurements and instrumentation. We have seen the functional elements of an instrument. We have talked about instrument types. We have talked about the performance characteristics of instruments, what an actual instrument should do, and what would be the measuring parameters for those instruments, and how we can actually compare them, and all those things. Now this is where we start with the basic principles, physical principles that are actually used in the design of these sensors, and the associated signal conditioning that we generally encounter in these types of systems. So we are now having module 2, module 3, and module 4. In the module 2, we'll be talking about the the various types of sensors that are used in the design of the instruments, and the signal conditioning will be taken up in the next half of this in this module. So moving ahead, so this is a typical example, automobile, in which you can see so many actually sensors are actually used. This is to give you an idea about the amount of sensors that are used, the number of sensors that are used in the modern automobiles. And this is just to give you a glimpse of that, because why do we go for so many sensors? It's not just about putting it more just for the sake of sensors, but it is actually because sensors are primarily used for monitoring and control purposes, and we would really want to improve upon the efficiency of the car, or the on the other aspects of the car, for example safety and other features of the car. Because of that, we would actually like to have so many sensors. New and new sensors are coming up, and then actually trying to make these systems better. For example, we have something called as coolant level probe. So you have a coolant level probe that automatically tells you that the level of coolant is actually decreasing, or it's fine. You have a temperature sensor, you have ABS, you have throttle control, you have turbo actuator, speed, position, and pressure sensors are installed. You have airflow sensors that are installed before the engine, because you need to have the amount of air that you are actually pulling in. It depends, because you may be at different places where the density of air is different, so the amount of air may be different. So to have a proper air fuel mixture, you need to actually measure and then calculate accordingly the amount of fuel that is to be put in. Similarly, you have tire pressure sensors, you have fuel sensors, you have so many other sensors that are actually put up in the modern automobiles. So this tells you about the demand of actually the instrumentation actually in the modern, contemporary world, where you would like to actually design new instruments, better instruments, actually to make things more efficient. Now let's come to the formal definitions. So a sensor is a device that receives a stimulus in the form of an input physical property and converts it often into an electrical signal that is compatible with the electronic circuit. So some of the books and some of the authors actually talk about sensors being more of those nature which convert one form of energy into an electrical energy, particularly that is called as sensors. But sensors and transducers are mostly analogously used. You may see sometimes somebody calling it as a pressure sensor or a pressure transducer. So both could be sometimes used analogous, but transducers are mostly talked about when we say we convert one form of energy to another form of energy. Those are the transducers. But sensors are a broader category which may include transducers also with them. So that's why we say sensor is often analogous to the transducer, or it could be the combination of transducer and signal processor. So in a transducer, which could be just primarily for the energy conversion from one form to another form, but the sensor could be including the signal processing and the amplification and other things that finally converts it to an electrical signal, which is actually compatible with the electronic circuits, because actually we are finally more interested in the monitoring and the control aspect of this. So this is a typical force sensing register, FSR we call it. So this is, again, you can say force sensor, we or a pressure sensor. We press with a thumb on this face, and then it changes the resistance of this, and accordingly it can be detected by Wheatstone bridge, can find out the amount of pressure that has been applied. So this is for us as a sensor. Similarly, there's a proximity sensor which is inductive based. We have a Bourdon tube gauge, a very common sensor, but in this case you might see in a different form that you have a Bourdon tube but then with an LVDT attached to it. So till now we had seen an example where a Bourdon tube was there and then there was a linkage mechanism that was a pointer that would point out to the amount of pressure that is in the measurand. But we can always use, for that displacement, rather than using a linkage mechanism, you can use something called as LVDT or any other type of position sensor, and then which converts basically into the electrical signal, which is actually fed to the electronic circuits for control purposes. So now this could be also called a sensor because you have an electrical signal at the output. Bourdon tube could be a transducer because it converts pressure to the displacement of this. So this could be this could be the transducer, this could be the electric circuitry, and then the complete could be the pressure sensor. This is how it looks like as a pressure sensor, but this is rather than using a Bourdon tube, we use something called as piezo resistive sensors or other type of semiconductors. It is a diaphragm that is there and whose actually deformation we are able to measure with some. We'll talk about those type of circuit, those types of sensors. But this is how a typical industrial, can say, or a commercial pressure sensor looks like. This is used for differential pressure measurements. So these are some of the sensors that we usually see in our day-to-day life or in the industries. Now, that's what we have just seen, that sensor could be actually composed of different transducers together along with some direct sensors, which finally leads to an electrical signal or an electronic signal. And this is the stimulus. So in the Bourdon pressure gauge, if we just see as per this block diagram fashion, so this is the gas supply or any other fluid that is whose pressure is to be measured, and this is the copper tube, or it could be any other tube that we have used as the transducer. So this converts the pressure of the gas into the displacement of this Bourdon tube. So what we have is pressure being converted to displacement. So that is transducing. So pressure converted to displacement, let's say D. Now, because of this linkage mechanism, this converts this displacement, or you can say linear displacement, into the angular displacement of this. So this is again kind of linear to rotary displacement. So we can say that this whole pressure gauge or the pressure sensor is actually composed of two transducers together to finally give us an output. Similarly, you have strain gauge base load cell, where we apply a pressure, and then we have a member which is the steel bar here, and we put up strain gauges on the steel bar in different ways in the form of strain gauge rosette, and then we try to measure the strain on the member or the stresses that are that are on the member. So in this case, again, the pressure that we apply or the forces that we apply actually cause the deformation of the steel bar. So that is kind of this steel bar itself is actually acting as a transducer, and then this deformation is actually converted into the change in the resistance of the strain gauge, which is finally converted to an electrical signal, or it can be taken up in the Wheatstone bridge. So again, we have another transducer. So again, a couple of transducers completely making it as a sensor for strain measurements. So we have seen that a sensor could be composed of transducers, a couple of transducers, or a sensor could be composed of a transducer and the signal conditioning, or they can say signal amplification. But mostly, say when we talk about sensor, this is actually nowadays in contemporary world, we say the sensor, generally are those that receive some stimuli and actually convert it to finally an electrical signal which is compatible with the electronic circuits. So this is very important in the contemporary arena. Now let's look at some of the typical examples of transducers, or you can say sensors here. So we have seen this table already in our earlier lecture. I have just reproduced here from the book. So for example, you have a thermocouple. So the input variable is the temperature, which is the measurand. We want to measure the temperature. The output value of the transducer is the voltage. So this is again, this tells you about what basically a sensor does. Actually, a thermocouple actually measures temperature, but it gives us in the form of a voltage. So obviously, liquid in glass thermometer could also be kind of a transducer or a sensor because it gives us temperature in the form of displacement. Now this displacement is seen visibly. This is just for monitoring purposes, but if we want to control this thing, so we can obviously convert this displacement into some position measuring instrument like an LVDT, which converts this displacement actually into the electrical signals, which can be used for control purposes. Similarly, resistance thermometers are used where temperature is converted into a resistance change, and all these other instruments or the sensors. A venturimeter is, again, you can say, a flow sensor. We measure the flow rate via change in the pressure levels. Similarly, other examples, Borden gauge, the pressure is converted to displacement. Obviously, this displacement can be taken up in the form of an other sensor which can actually measure convert this into an electrical signal. Piezoelectric devices, the forces that we apply are converted to voltages. And resistance strain gauges, similarly, we have force being converted to change in the resistance. Similarly, we have so many examples of these transducers or sensors that are used, and different types of physical principles are actually used. This is the physical principle that is mentioned here. So for example, you have a Hall effect sensor. We'll talk about this in detail. So this converts a magnetic flux or the current into the Hall effect voltage change. Now the principle is that Hall effect voltage is produced across semiconductor plate in the direction perpendicular to both impressed magnetic field and the applied current. So maybe a little simpler, I'll just talk about the principle that we use in Borden gauge. So you have a pressure being converted to displacement, how the application of pressure causes displacement in the elastic element. So this is the physical principle that we are used, or that we use, which is behind the this is the principle behind this sensor. Similarly, all other, for example, if we talk about a spring balance, simple spring balance where the force is converted to displacement, the application of force against a spring changes its length in proportion to the applied force. So this is the principle. So we have principle of operation, we have type of device or the sensor, and these are the input value variable and the output variable of the transducer. Now these tables actually tell you about, maybe give you a good variety of devices or the sensors that are used, and these are quite very popularly used. And you have maybe some other, we have put up here 24 different sensors that are used, and we can have obviously more than that. And we need to be careful about the different types of varieties that are available, the different physical principles that are used, which can be used in the design of new instruments. Now let's talk about the classification of these of the sensors that we generally encounter with, or that we generally have available to us. So we have capacitive and resistive sensors. So obviously this classification is based on the basic physical principles that they use. So one of them is capacitive and resistive sensors, which are more related to capacitance and resistance of the sensors that we are using, or the elements. Then we have magnetic sensors, which are more of inductive based, the principle of magnetic, you can say, induction that we have. Then we have piezoelectric sensors using piezoelectric principles. We have Hall effect sensors, which use the principle of Hall effect. We have optical sensors, which are based on the light. Then we have ultrasonic transducers. Obviously, the more popular way to classify them is ultrasonic transducers. We can say ultrasonic sensors also, I think, but transducers is more suitable for ultrasonic. Then we have nuclear and micro sensors. So this is the broad classification of the sensors that we will study, and that is generally covered. Though we may have some other, let's say chemical and other things also for the sensors. But we are more interested actually into the sensors that are used in the engineering arena and that have an electrical output at the end. Now let's come to the capacitive sensors. So as the name implies, this is more related to the capacitance of the the sensor that changes as we change different parameters. So obviously, as the capacitor, we have studied that it's nothing but consisting of two metal plates in which a dielectric is placed between the plates, and the capacitance is given by epsilon naught, epsilon r, a by d, where a is the area of the plates, d is the distance between the plates, and epsilons actually refer to the dielectric constant, or you can say the absolute permittivity and the relative permittivity of the dielectric medium between the plates. Now, with this principle in place, because of the advancements in the you can say manufacturing capabilities at the micro level, at the nano level, we're able to design these capacitors, or we're able to design such capacitors, which can be designed at the micro, or you can say at the million level, where we can use them as sensors, because we can change the capacitance of a given, let's say, you can say a given, a given sensor, by changing the area between the area of the plates, or you can say the distance between the plates, or the permittivity between the of the dielectric medium. Now they are obviously used as displacement sensors, in which we can use them by changing the distance between the two plates. We can measure the distance, or we can measure the change in the capacitance. Accordingly, they can be used as displacement sensors. The measuring, often the measure displacement is part of the instruments measuring pressure, sound, and acceleration. So obviously this displacement measurement can be part of the measurement of pressure. We are actually trying to measure the pressure using a diaphragm, and as the diaphragm displaces or moves, so accordingly, which could be part of the plates of the capacitor, accordingly the distance between the plates can change, which can be calibrated to the amount of pressure being applied on the diaphragm. Similarly, sound or acceleration, all these things we can use capacitive sensors. Now they can obviously they have a considerable application in the industries, where we can actually change the dielectric between the two plates, also by putting something called liquids or something like plastic. All those things can be put up, so that we can use them in the industries, packaging industries, where we can actually monitor the amount of let's say the type of liquid that is present in the, for example, in this milk cans, is there any contents of glass, or in any contents of plastics. All those things actually will cause change in the capacitance, because that acts as a dielectric medium. Similarly, fixed plate capacitors can also be used as sensors, in which the capacitance value is changed by causing the measurable variable to change the dielectric constant of the material between the plates. So this can be used to monitor the liquid level and other features or other parameters. For example, if you see this sensor that is placed inside the liquid tank or the water tank, you have a minimum liquid level and a maximum liquid level that is given here, and you can actually put up two capacitive plates. So this is the dielectric, this liquid acts as the dielectric here. So this liquid here is the dielectric, obviously that comes in between the plates also, and accordingly the capacitance changes, and we can actually measure that with a microcontroller. We can put this, get these signals, and accordingly we can display the value of the capacitance. So the change in capacitance can be equated to the amount of liquid level in the tank. All right. So these are some of the applications of capacitive sensors. And then we have resistive sensors, and obviously this is more about the resistance of a material. When we change the material, or sorry, we change the resistivity of the material, or we change the length of the material, or we change the area of the material, and accordingly its resistance changes, because the resistance of a metal conductor or an electric conductor, as we generally refer to it, is given by rho L by A, where rho is the resistivity, L is the length of the conductor, and A is the area of the conductor. So similarly, if we somehow are able to change the area, we can change the resistance. If we are able to change the length, we can change the resistance, and if we are able to change the resistivity also, and we are able to change the resistance. So this change in resistance can actually be calibrated to then those changes. So many sensors are now based on these principles. There could be sliding contact device like potentiometers. All right. So where you just change the length of the resistor that comes in part of the circuit, so accordingly the resistance changes. Or it could be resistance strain gauges, where you change even the length, area, and the resistivity, and accordingly the resistance of the strain gauge changes. You have another class called thermistors or RTDs, that is resistance temperature detectors. You have photoconductive light detectors, which is something popularly called as LDRs, and you have piezo-resistive strain gauges, where rho actually changes, and accordingly the resistance changes. That change in resistance can be can be correlated or calibrated to the amount of the parameter that is to be measured. Now in the resistive sensors, we have sliding contact devices, resistance strain gauges, thermistors, and or the resistance temperature detectors, that is RTDs. And then we have piezo-resistive strain gauges and photoconductive light detectors. Now, coming to sliding contact devices, sliding contact devices are very popular and similar that we have seen in the physics labs, or you can say in the basic electrical engineering courses. So the mechanical displacement now is converted into electrical output because it causes changes in the resistance, because it's nothing but a kind of a slider moving on a resistive kind of a wire, where it changes the amount of the length that comes in, becomes part of the circuit, and accordingly it changes the resistance of that part, and then we get the amount of displacement that has taken place. Obviously accomplished by changing the effective length of the conductor. Now obviously we use some form of electric resistance element, and then the simplest form, it could be a stretched resistance wire and a slider. We'll just see it now. So devices of this type have been used for sensing relatively large displacement, and more commonly they are formed by wrapping a resistance wire around a foam or card. The turns are spaced to prevent shorting, because there could be shorts between the turns. It could be something like this that is here told, and the brush slides across the turns from one turn to the next. So in practice, it could be again formed in the form of a rectilinear movement, or the resistance element may be formed into an arc, and angular movement is used. So this is how it looks like. You have a slide or brush, or a slider or a brush. You have a resistance wire. You have a guide rod. So this you can connect to your object that whose displacement you want to measure. As this object moves, this slider also moves, and accordingly it changes the point of contact between the slider and the resistance wire, which actually takes up the amount of resistance as per R is equal to rho L by A. Fine. And these are some of the line diagrams of the translatory type, a rotary type, and a helipod type. This is how it looks like in practice. So you change this slider, make it move front and back, and accordingly the resistance changes, and you can actually calibrate it with the scale also. Now they can also be made using conductive films as the variable resistant elements rather than wires. Common examples are the carbon composition films, in which we use graphite or carbon particles which are suspended in epoxy or polyester binder. Or it could be ceramic metal composition films, in which ceramic and precious metal powders are combined. So in all these cases, it's backed by plastic, layers, which actually tries to support the carbon composition films or the ceramic ones. Now they are generally less expensive than wire-wound devices and have outstanding wear characteristics and long life. But the disadvantage is that they are susceptible to temperature drift and humidity effects. And these are generally called as pots or potentiometers. Now, you could have sometimes multi-turn pots also. We'll see it here. So this is how it looks like. You have a wire-bound resistance element. It's the normal one that we see, but this is more of a plastic or ceramic backing, and then a conductive carbon composition film that is put up here. So as per the slider or the brush, as it moves, as per the rotation of the object whose rotation is to be measured, or whose angular motion is to be measured, accordingly the slider or the brush moves and comes in contact with this carbon film composition film, and accordingly the amount of resistance is changes, and we can calibrate it to the rotary motion of the device or the object that we want to measure. This is how it looks like in real, I can say, practice. So this is how it looks like. You have 3 terminals, and then you have a multi-turn pots which can be used, though we have generally these pots are actually only having a range of 0 to maybe 180 degrees or more than that, but we have these days something called as multi-turn pots also. These are sometimes in this form, and also in this form. So now these types of pots can be used in the circuits where we want to have a variable resistance, and we can change the resistance if we want to do it according to our requirements by just rotating this screw here. Accordingly, it will change the resistance between the two ends. So this can be also used in circuits where we want to have change the resistance without actually changing the the resistor itself. So we have something called variable resistance kind of pots. Similarly, you have resistance strain gauges. So obviously we have, this is more of a fine wire which is cemented on the surface of a member to be strained or put under strain. This is what we popularly see it this way. So nothing but again a resistance element whose resistance changes as the area also changes, the length also changes, and the resistivity also changes. So we have something called gauge factor and other things that we take together actually in deriving the equation for this strain gauge. So obviously on the application of strain, the length, area, and even the resistivity of the wire would change, and this resistance change is actually equal, or you can say equated to the strain on the member. We use something called as Wheatstone bridge to calculate the change in the resistance and corresponding strain in the member. Now this principle of all these actually follow the principle of variable resistance, or the change in the resistance. So that's why we call them as capacitive and resistive sensors, where we actually use the principle of change in resistance in designing these sensors. These are very helpful for us to determine the stresses and strains on the members. This is how it looks like. You have a gauge resistance wires, you have a gauge backing on which they are put in, then you have direction of strain. Accordingly, you have change in the resistance that is put up here in the Wheatstone bridge. And accordingly, you correspond the change in strain to the amount of strain that is actually occurring on the member. This can also be used to find out the stresses on the human bone. If you load the human bone with some, let's say, kind of forces, and you can easily calculate the amount of strain that is caused at different locations on the human bone by putting something called a strain gauge rosettes, where we have strain gauges in almost, you can say, 3 directions. Similarly, we have obviously the application, the structural members, where we want to find out the strain on a member by again putting some strain gauge rosettes and loading it with some value, and accordingly relating the strain or the change in resistance to the strain on the member. Now we have another class called thermistors, which is we have thermally sensitive variable resistors. It's like made up of ceramic like semiconducting materials. So thermistors, we have something called as semiconducting materials. They are a type of semiconductor, so they have a greater resistance than conducting materials, but they have lower resistance than insulating materials. So obviously they are in between the conducting and the insulating one. So they are made up of semiconductors. So oxides of magnesium, nickel, and cobalt are used in the formulations having resistance of 100 to 450,000 ohms. And they are generally of 2 types, with NTC, that is negative temperature coefficient, and you have positive temperature coefficient thermistors. So in the negative ones, the resistance decreases as the temperature rises. You have this type of thermistors also available. This is because we have semiconductors. These are the basic elements of the semiconductors, which can be actually designed in such a way that they have a negative temperature coefficient, or you can say the resistance of those semiconductors decrease as the temperature rises. And then we have another class called positive temperature one, in which it's vice versa. The resistance increases as the temperature rises. The main applications are in the current limiters, temperature sensors. We use them in circuit boards, where we use NTCs generally in temperature sensors or current limiters. And similarly, you have self-resetting overcurrent protectors and the self-regulating heating elements, where we use PTC types. So as temperature detecting elements, they can be also used for the purpose of measurement and control. And electric power sensing devices, they can also be used as electric power sensing devices, where the resistance is a function of the power being dissipated by the device. So you should take in mind that thermistors are actually more of composed of actually semiconductors. So, and they are mostly used in the circuits, electronic circuits or electrical circuits. So this is how they look like physically. You have bead thermistor, you have disc thermistor, glass probe thermistor, and you have washer thermistor, special probe assembly thermistors. So all these are having considerable application in the electrical and electronic circuits, where we want to actually limit the current going through a circuit, because it can really damage the circuit. So as the current increases, obviously the temperature increases because of the I square R losses, and accordingly as the temperature increases considerably, so we can measure this with these thermistors, and we can either design them in such a way that they themselves burn and then they are taken as a part of the circuits, and the moment they burn off, then the circuit is obviously open, so our rest of the circuit is saved, or we can use them or maybe convert them into some electronic signal and then accordingly take some action on the safety of the circuit. Then another part of the similar thermistors is resistance temperature detectors, or RTDs. So obviously it's again a sensor whose temperature or resistance changes with the temperature. So they're typically built of platinum wires wrapped around a ceramic bobbin. So its behavior is more accurate and more linear over wide temperatures than that of a thermocouple. So another one is thermocouple, where we have two dissimilar metals actually being combined. So we'll talk about that later on. But this is just to give a difference between the two, actually, why sometimes RTDs are preferred. But because RTDs are part of the resistance change, so that's why we have classified them into the variable resistance type of sensors. So because we have a platinum wire that's wrapped around a ceramic bobbin, so because platinum has a well-defined temperature resistance relation, more of a linear relationship between the temperature and the resistance. So in the instrumentation, we measure the resistance and convert it to the temperature measurement using temperature versus resistance calibration data. So the cost of these is not generally higher than thermocouples. They use copper leads, and obviously we have to trade off between the use of thermocouples or the RTDs. So obviously they don't require any kind of junction. So obviously they are having some advantages in terms of their usage and their application and their deployment, but maybe in terms of cost they are expensive. This is how it looks like. Now they are also fast replacing the thermostats that we use in the electric geysers because of their platinum being used, and their linear relationship between the temperature and the resistance. So we can easily find out the change in the temperature of the element that we want to measure. This is how it looks like from inside. So you have platinum wires / platinum sensing wires here wrapped around like this, and then this is the other parts of the assembly that is put up in these RTDs. Why I have put it up here, because this is part of the resistance change, because the resistance of these platinum wires change as per the temperature, and it's having a linear relationship. So that's why it was classified into the variable resistance sensors. So this is a graph of the thermistors, RTDs, and thermocouples. So we are not studying thermocouples till now, but if we compare thermistors and RTDs, so this is how thermistors would look like. You have temperature versus resistance graph. So this is the resistance, this is the temperature. So you have a sharp decrease in the, or you can say sharp increase in the resistance as the temperature drops in the thermistor, but RTDs have almost a linear relationship over a longer range of temperature with the resistance. So that's why they are fast replacing thermocouples. But obviously thermistors are more often used in the electric circuit. So whether we want to use this or that, it really depends. We may have thermistors really being compact, and that's why they are all used in the electronic circuits. So obviously each have their own applications. Then we have piezo-resistive strain gauges. They are not actually piezoelectric, which we actually referred by the name, but rather they are again strain gauges. They have similar applications, but the strain gauge is not made up of a conductor here or an electric conductor here. Rather, it's made up of a semiconducting material, so as the sensing element. No, these are made by doping some P and N type of let's say semiconducting materials, and then this type of element is used in place of strain gauges and put up to measure the strain. So what happens is, again, a deformation occurs in the crystal lattice of the diaphragm, which is used on which this strain gauge piezoresistive is put up, because of obviously bending, or you can say other types of deflections or deformations, and this causes obviously a change in the resistivity of the material. So piezoresistive is more about the rho part. So we have R is equal to rho L by A. The piezoresistive, or you can say photoconductive, and others are actually more about the rho part, or even you can say thermistors. So in thermistors we don't expect change in L and A. In the piezoresistive we don't expect change in L and A, and similarly in the photoconductive we don't expect change in L and A, but it's more about change in the rho, and obviously they are more about temperature dependent. So temperature will not cause more changes in L and A, but temperature actually will cause changes in the resistivity of the material. So obviously we make some semiconducting materials out of some NP type, This deformation actually will cause a change in the band structure of the piezo resistors, and which leads to change in the resistivity of the material. So in the thermistors, it's more about temperature. In the piezo resistor, so I'll just put up here rho changes in all the cases, that is thermistors, piezo resistive, and the third one is our photoconductive. So in the thermistors, so in all these cases, we have in L and A does not change much. Thermistors, it's temperature actually that causes change in the rho. Piezoresistive, it is the deformation that causes change in the rho. Photoconductivity, it is the light actually that causes change in the density. Sorry, in the resistivity. So this change can be an increase or a decrease according to the orientation of the resistors, and they are all used in similar procedure to the strain gauges, where a bridge circuit is actually employed to measure the change in the resistance due to the deformation. So piezoresistive strain gauge and strain gauge are similar. The only thing is the material used in piezoresistive is different, and obviously it is more of the change in the resistivity rather than the length and the area that is caused by the deformation, and that is actually what is measured. So obviously, similar to metal conductors whose resistance change is accounted for the change in length, area, and resistivity in piezoresistive sensors, is mainly due to the resistivity change of the semiconducting materials used as the basic elements of the sensors. Have wide applications in biomedical, automotive, and household appliances, mostly as piezoresistive pressure sensors. So in semiconducting materials, the piezoresistive effect actually dominates than the metals, in which the other effects also in the form of deformation, the change in length and area, is there. But in the semiconducting materials, the piezoresistive effect, that is change in the resistivity, actually dominates, and it's typically being orders of magnitude rather than the contribution from the geometry, that is change in the length and the area. And most commonly, silicon can be used to measure these strain gauge pressure sensors, and it can be adjusted. The characteristics can be adjusted by doping, changing the doping levels. You can have higher doping, lower doping of P and N type. The controlling carefully the amount of impurities to the semiconductor. So more lightly doped silicon results in higher resistivity and a higher gauge factor. However, the only disadvantage is that it increases the thermal sensitivity of both the resistance and the gauge factor. But in some metals like platinum alloys, the piezoresistive effect can increase the sensitivity by a factor of 2 or more. This is how it looks like. You have applied pressure here, and this is the diaphragm on which this piezoresistive metal is actually put up, or the semiconductor is put up, and while deformation due to the applied pressure actually causes deformation of this diaphragm, and because of the deformation of the diaphragm, it causes change in the crystal structure of this piezoresistive element, and accordingly it changes the resistance of this, because it causes change in the rho, that is the resistivity. Change in the resistance is actually picked up by the Wheatstone bridge, and we are able to calibrate this change to the amount of pressure being applied. And the last one is photoconductive light detectors, or we may have heard about LDRs, light detecting resistors. So they are again a type of photodetectors which are based on photoconductive semiconductor materials. The absorption of incident light actually creates non-equilibrium electric characteristics, and this reduces the electric resistance across the two electrodes. So obviously this is more about light dependent. This again changes the rho, that is the resistivity, but this is actually because of the absorption of the incident light that is put up on those semiconducting materials. So alternate terms are photoresistors or light dependent resistors, that is LDRs, or photocells. Now they are particularly sensitive in the infrared region, and for detection of visible light, one would usually prefer photodiodes due to their clear superior performance, but photoconductive detectors are often used as infrared detectors because they are more, I can say, they are particularly sensitive in this infrared region more. This is how it looks like in practice. These are the LDRs. So as the light is incident on them, the resistivity changes, and accordingly this can be picked up by again a similar Wheatstone bridge, and you can actually calculate the intensity of light that is put up. So these are quite useful in various applications that we can think of. But again, why this has been put up in this class is because we are talking about the variable resistive sensor. So again, the resistance changes because of the photo, that is the light incident on this type of semiconducting material. So this is about the first class, that is variable resistance and variable capacitance. We'll look at the variable inductance or the magnetic sensors in the next lecture.